All right, welcome back to Physics 9B. So today we will learn more about thermodynamics. What you're looking at is a molecule. It has the same shape as water, H2O. And what you're seeing here is that we live in 3 dimensions. We can move front and back, left and right, top and bottom. So these are the 3 ways a molecule can translate. Translate means just changing its position. There are more complicated things that a molecule can do, such as rotation. And because we also live in 3 dimensions, there's also 3 ways you can rotate. You can rotate around the y-axis, the z-axis, and the x-axis. So microscopically, even though you don't know the shape of the atom by looking at a cup of water, this detail of the motion they can do will affect their behavior. More specifically, it will affect their molar heat capacity. You guys have enough with molecules? So, when we compare, let's say, a monatomic gas, helium, neon, argon, xenon, those are monatomic gas, which means the molecule only have one atom. When you only have one atom, it's a point. An atom is very small. It basically only have a point, and there's no internal structure in the sense that if you rotate it, rotating a point doesn't do anything. Rotating a point still gives you the same point. So for monoatomic atom, we say they only have translation. It can only move from back, top, down, left, right. Compared to a molecule with multiple atoms, such as triatomic, diatomic, they can do a lot more stuff. They can rotate, they can vibrate. Those will give some effect, and that you can observe microscopically. But for here, I hope you all understand that there's a difference between monatomic gas and diatomic and triatomic. These can do a lot more things, specifically rotation and vibration. Rotation and vibration. They can all translate, but you cannot vibrate with one atom, and rotating one atom doesn't do anything. Okay? So, how exactly does this affect the thermodynamic? There's a thing called equipartition theorem because in the region of thermodynamics, things are so random. You don't know which one should have more energy. So at the end, they just average out and have the same amount of energy. Just like when you go to vote, everybody have the same amount of power when you are voting. The way to increase your power as a party is to have more people in your party. So even though under randomness, translation, rotation, and vibration are all the same, but if a single molecule can do more things, they can start up with equal weight. So let's say they are immersed in an environment with energy T. What the equipartition theorem says is that when you have a way to have energy, that way of having energy will give you 1/2 kBT of energy. kBT has the dimension of energy, and we learned that it has the meaning of average energy. And here we learn that because the average energy under a temperature is kBT divided by 2. The more way you can have the energy, the more energy you have. So under the same temperature, a monatomic atom can only translate. So it will have less energy than a triatomic molecule, even though they're under the same temperature. Because for a triatomic molecule, it can have energy in the form of not just translation, but also rotation and vibration. So together, if you just look at one atom on average and a triatomic molecule, the triatomic molecule will have higher energy even though the temperature is the same. Does that make sense? Okay, so while we are talking about this, the hot water is ready. What's in front of you is a heat engine, which we have hot water, and the hot water will stop flowing after I finish pouring the water, so there will be no displacement. In order to do work, you need to have displacement, which this hot water is not going to have. Therefore, there's no way the hot water can give energy to this propeller in the form of work. But what you will see later is that it will start rotating, and that will be exchanging energy with heat. Are you ready? Good. So air friction is taking away energy. In order to keep the rotation, energy must enter from the bottom to the top in some way. That form is not work because there's no displacement. There's no macroscopic motion between anything. But we learned that there's a different form that you never learned in 9A called heat. So now heat is going into this heat engine, and the heat is turning to work into the work that rotates the propeller. We'll talk more about it in the end of the lecture. For now, let's focus on the equipartition theorem. Let's say we want to raise the temperature of the gas by a delta T. To do that for a monatomic atom, we only need to increase the energy in the form of translation, because that's the only form of energy that a monatomic atom can have. On the other hand, if you have triatomic molecule, you have to equally put the same amount, you have to equally put energy into both translation, rotation, and vibration, because that's what equipartition theorem tells you. They are equal in the sense that you must treat them in the same way. If you want to increase the energy in translation, then you also have to increase the energy in rotation and vibration. And here, the height of the water level is like the change of temperature, which is visible. And if you have more mode of energy, it's like you have more bucket that you need to fill in order to increase your temperature. So what you will see is that in order to increase the temperature of monatomic gas by delta T, you add in this amount of heat. And for increasing the temperature of triatomic molecule by the same amount, you have to add in possibly different amount of heat because you have to fill in more buckets. So you should see that in order to increase the temperature by the same amount, it's easier to heat up monatomic gas compared to a triatomic gas, because to increase the temperature of triatomic gas, you have to increase the energy in translation, rotation, vibration, all of them. Okay? Any question? So for now, for the midterm, you don't need to count exactly how many ways of rotation, translation, and vibration they can do. That will be for the final. For now, you should know that there's more ways for triatomic molecule to have energy, so it's harder to increase the temperature. In that case, which one will have a bigger molar heat capacity? What is molar heat capacity? It's the amount of heat you need to heat 1 mole of that gas by 1 degree Celsius. So if you have a bigger molar heat capacity, it means you need more heat to increase the temperature by the same amount. So which one is harder to heat up? Is it easier to heat up monatomic gas, which you just need to increase the translational energy, or you have to increase translational energy plus rotational energy plus vibrational energy? Which one is easier? The answer is B. Because for triatomic molecule, increasing temperature means increasing the energy in the form of both translation, vibration, and rotation. It's harder. You need more heat to increase all of them. So that means a bigger molar heat capacity. Any question? Good. So equipartition theorem is a classical theorem In reality, the amount of mode of a molecule is not determined just by the atomic, not by the molecular structure. It also depends on the temperature. This is because different modes, even though they all contain the same amount of energy when excited, the difficulty to excite them is different. It is very easy to move something, it's easy to translate something, but it is harder to excite the rotation. So in the beginning, if the temperature is low, you might have a triatomic molecule, but only the translational mode is excited. So if you measure the heat capacity at low temperature, the translational energy is the only one that got excited. So under low temperature, monatomic gas and triatomic gas will have the same molar heat capacity. But as you increase the temperature, the rotational mode get excited, and the triatomic gas start having a higher molar heat capacity. It becomes harder to increase its temperature because now you have to fill in the bucket, not just in translation, but also rotation. Vibration, at the end, will be the hardest to excite. So if you further increase the temperature, you will see another increase in the molar heat capacity of triatomic molecule, because in the beginning, at low temperature, the molecules can translate, can rotate, but they don't vibrate. It's harder to excite the vibrational energy. Intuitively, I hope you can see it's easy to translate, it's easy to rotate, but it's hard to vibrate. When it vibrates, it makes a sound, and you don't see the noise right now because it's hard to excite vibration. But exactly how hard it is quantum mechanics, yeah?
How come vibrations are hard? From what I understand, like the molecules and solids, they just only vibrate. They don't translate or rotate.
That is solid, which is a molar molecule. Just increase the triatomic molecule with more thing in the front. It is a molecule with 6 to the 10 to the power 23 atoms. In that case, there are some vibrational modes that is equally easy to excite compared to translational mode. So you will see this plateau, or you will see this jump happens earlier. But for a single molecule isolated with only 2 atoms, quantum mechanics will tell you the vibrational energy is higher than translational one. Translational one can be as low as possible depending on the box you put it in. The bigger the box, then the energy level basically becomes continuous. But to vibrate it, there's a finite jump, and you can measure it by measuring the spectrum. That spectrum tells you you need a certain amount of energy to excite vibration, and that energy scale tells you what temperature will it be excited. Good. Any other question? You won't be questioned on quantum mechanics in this class, but they will tell you you have a triatomic molecule with vibrational mode frozen. Now you need to understand that means the mode it has only here is only here, and you should use the molar heat capacity at this plateau for the calculation. Okay. So that is mode counting and equipartition theorem. This is the first quantum effect you can possibly observe in human history. You are just measuring temperature with your measure stick and some heater. But when you see this curve, it tells you the molecular structure, which is in a scale of 10 to the minus 10 meter. That's amazing, right? You can measure you can tell something that's small just by measuring the heat capacity. So next we enter the application part of using heat and the thermodynamical process. To make this heat engine or to design a better one, we need to study how a process works when a heat or some heat is involved. The first terminology we introduce is something called quasi-static, meaning it's really slow. When the process is really slow, such as the top one, I am compressing the piston in a really slow rate. So every instant, the gas is distributed evenly. They always have enough time to reach equilibrium, even though I am changing the volume. On the other hand, if I push the piston with a high speed or high rate, the molecule will accumulate on the wall of the piston, right? So that means at the intermediate stage, the molecule doesn't have time to reach equilibrium again, and that is what we call not quasi-static. Basically, if you do something really fast, it's not quasi-static. If you do something really, really slow, then it's quasi-static. The more slow it is, the more quasi-static it is. If you are static, it means you're not moving. So quasi-static means really slow. Okay? Any question? Yeah.
Sorry, can you just like explain that like just all again? Sorry.
So the top one will happen when you push the piston really slow, because if you push the piston too fast, the atom that was originally at here will be pushed and accumulate on the piston. If you push it slow enough, the gas will have enough time to bounce to the other side and distribute inside the box in an even way. But if you do it real fast, then there will be a significant difference of the distribution of the gas molecule in the box. Okay? Any other question? Good. Now, it's your turn. This process is different. The reason we call them different names is because they are physical consequences. If you compare pushing a piston real fast and slowly, which one requires more energy to do that? Does it take more energy to compress it real fast or slowly compress it? Your total displacement is the same. Work is force times displacement. You are doing the same amount of displacement, so that's not where you should consider. What you should consider is how the accumulation affects the pressure on the piston. You learn PV equals NKBT, so the more molecule you have, the higher the pressure. Similarly, if you have an accumulation of gas over here, a lot of gas is bouncing on the piston, pressure becomes higher compared to the slow pushing one. So you are pushing the piston in a way that the pressure is always higher than slowly pushing it. At every stage down here, the pressure on the piston will be higher than slowly pushing because the gas is accumulating here. There's more gas hitting the wall compared to the slow pushing one. So at the end of the day, the way you push the piston will affect the amount of work you do to change its position. If you push it real fast, you will have to do more work. Okay? Any question? Good. Quasi-static? Not quasi-static. So let's skip this one, which I forgot I'm going to ask you. Now, let's think about a reverse process. Here, instead of pushing a piston, I am letting the piston move and expand the gas. The gas is pushing the piston and do work to the environment. On the top side, the piston is moving really fast. You can do that by having a light piston. At the bottom one, your piston is moving really slow. You can do that by increasing the mass of the piston, so there's big inertia, it will move really slow. But you can assume both of them have no friction, so they can always be pushed. But the top one is very light, the bottom one is really heavy, so the top one gets accelerated real fast and move really fast to the right, and the bottom one moves really slow. So compared to the bottom case and the top case, which gas will do more work on the piston and release more energy to the environment? Again, the key is the distribution of gas. On the top, the gas doesn't have a chance, doesn't have enough time to distribute evenly again to the right of the wall. You need to have gas particle bouncing off the piston to create pressure. Here, some of the molecule might be able to make it to the right, but most of them don't have time to reach the piston yet if you move the piston really fast away from the gases. So on the top, you'll create an area with small pressure compared to the bottom one, and when the pressure is small, you have a smaller work overall. So the bottom one will have more work done to the environment. Pay attention to the difference. Here, the quasi-static one do more work compared to the previous part. The non-quasi-static one do more work. See, it's not about quasi-static or not. You really have to think about how the gas get pushed to figure out which one resulting in more work to the gas or the environment. It's not quasi-static more work, no. Here, when you have non-quasi-static process, there's more work, but for here, the quasi-static one do more work. So it depends, okay? Any question? All right, so that's the meaning of quasi-static, just a terminology. It's really slow. And the gas and the state is always at somewhat equilibrium. The next terminology is called reversible, which means you can reverse the process. So let's consider a gas being compressed really slowly and then released also really slow. In this case, the amount of pressure of the gas is just the ideal gas law, PV equals nRT. The temperature is the same because I'm putting them in the same environment. The particle number is the same. So at each corresponding moment, as long as the volume is the same, the pressure is the same, then the work done by the gas in this direction, in this process, will be the same as the total work done by the environment to the gas in the reverse process. From here to here, the work is the same as here to here, but flow in different direction. Here, work flow into the gas. Here, work flow out of the gas. And the work flowing from environment to the gas from here to here is the same as the work flowing from the gas to the environment from here to here. So at the end of the day, after a cycle, the amount of work that flow out of the gas will flow back into the gas, and the gas return to its initial state with the same energy. So this is called a reversible process, and because the process is really slow, so it's also a quasi-static process. Okay? Any questions so far? Good. Now, let's consider a case which is not quasi-static. You can push the piston really fast, which makes the gas accumulate by the piston when you are pressing it. That will create a bigger work because the pressure is bigger. And if you also release the gas real fast, in this time, instead of accumulating on the piston, they will not have time to hit the piston, or they will not have time to reach the piston yet. So the pressure on the piston in the reverse process is smaller. So here, pressure is always bigger than the bottom. So overall, the work that flows into the gas when you compress it will be bigger than the work that flows out of the gas when you release it. Okay, because the process is so fast, the gas is not in an equilibrium state. The pressure depends more than just the volume, but also on how fast you compress it. So at the end of the day, you output more energy than the energy input back. So even though the piston is back to the initial position, the gas of the energy decrease overall because you flow out with a bigger work, and the work that flows in is smaller than the one that flows out. Okay? So you see that if a process is not quasi-static, then it will definitely be irreversible. You must have a quasi-static process to have reversible process. But just because you have a quasi-static process doesn't mean the process will be reversible. If you compress the gas again slowly, really, really slow, and then you wait a bit when the gas is in the smallest volume, then in this case, you can let the heat escape and the energy of the gas decreases, besides just by doing work to the environment. And then you can block this wall with some styrofoam or heat insulating material such that the heat cannot flow back in. Then even though the work done by the gas might be, so the work done by the gas will be different because temperature is smaller and pressure is smaller. But here you see that when heat is involved, quasi-static process can also be irreversible. So quasi-static is not always reversible, and not quasi-static is always irreversible. If you want reversible process, it must be quasi-static, but just because you're quasi-static doesn't mean you are reversible. Okay? Any question? Yeah.
So it's irreversible in this case because some heat is let out?
Yes.
Okay.
And that is not going to flow back unless you do something, but that is cheating. The thing you need to be able to go back to itself without the help of others. If you if you smash your iPhone and then buy a new iPhone, the process is not reversible. That doesn't count. Okay? Any other question? All right. So let's try to turn the process into a graph because it is hard to draw all these atoms. So it will be easier to communicate if we can read graph and communicate with graph. This is the pressure versus volume. Here you are compressing a gas, so the volume decrease, and the arrow tells you that you are going from point A to point B on a PV diagram, which the volume do decrease. And ideal gas law tells you that if you compress a gas, pressure increase, so the pressure goes up. And the reason you can connect these dots with a line is because every point on the line have a well-defined pressure and volume. What do I mean by that? If I have a process that is not quasi-static, then what exactly is the volume and pressure of the gas at this point? Well, it's not defined because you need to be in equilibrium to have a well-defined pressure and volume. Here you might have to define pressure point by point, depends on the different location of the gas, but overall, there's not a well-defined pressure for the entire gas itself. So if you want to draw this process, you will have to jump from A to C. You cannot connect them because you don't know what is the pressure of the gas at the between. There's no well-defined pressure and no well-defined volume. But you can have a final state, in this case, a bigger pressure, because we learned that if you press it real fast, the atoms will accumulate and the work you do will be bigger and those energy turns into a higher pressure under the same volume. Okay? Any question with this graph? So this is called a PV diagram, a pressure versus volume, a very common diagram to describe a process. The next common one is called a PT diagram, which you plot the pressure and the temperature of the gas together. If the number of the gas is fixed, PV equals nRT, you can convert between temperature and volume by a single line calculation. So one graph is usually enough. And for a quasi-static process, again, we have a well-defined pressure and temperature at every single state. And in this case, compressing gas increasing the pressure, and if you don't let the heat flow out, then the temperature will also increase. If you let the heat flow out, then the temperature will slowly decrease, but in this case, let's stop at point B. And this is a quasi-static process. Every point has well-defined state. Every point is basically in equilibrium. You can connect them. On the other hand, if you push it real fast, you don't have a well-defined temperature here. What's the temperature here? Well, if you stick your magic stick into different depth, it will read a higher temperature on the right, lower temperature on the left. So that's not a well-defined temperature for the entire gas. And you don't draw lines connecting the two states. You can have an initial state, and you can wait for the gas to reach equilibrium after you finish pushing the gas. But in between, if this is not a quasi-static process, there's no well-defined pressure and temperature, and you just jump from A to C. You don't connect them. Okay? So this is just drawing. In your final, you will be asked to know the function form of this curve, but for now, it's just a curve going up. So let's look at some nice animation of how the gas looks like when you are doing work to the environment. The gas are moving around, pushing the piston, and doing work to the piston. As the gas expands, the pressure decrease, temperature decrease, the energy decrease, so the speed of the gas decrease. Initially, it's moving real fast because the energy and temperature is the same thing. But then energy decrease, temperature decrease as you do work and lose energy. How exactly do we calculate this work? Well, in 9A, you learn that work is force times displacement. So you have this formula, F times delta X. In this case, we know the delta X of the piston is from down here to up here, but we don't usually talk about force for a gas. We talk about pressure. To convert them, we learn that pressure is force divided by volume, force divided by area. So if you multiply the pressure of the air times the area of the piston, then you get the force. Then you can combine the area and this delta X. Then you get the volume of the cylinder, which is the change of volume of the gas from this state to this state. So at the end, we have a way to compute work done by the gas using pressure and volume. The work done by the gas will just be its pressure times the change of volume. This works not only for a cylinder. If you have a balloon or irregular shape, you just need to calculate the overall volume change to get the work done by the gas, as long as it is a quite steady process. If you do some weird thing too fast, then it's really hard to calculate, and we don't do that. Okay? Any question with this formula? Good. Now, when you look at this process on the PV diagram, work equals P times the change of volume tells you that the area under this PV curve is exactly the work done by the gas. Note that the gas have to be expanding to do work to the environment. If the direction of the process is reversed, then work goes into the gas. You do work on the gas, not the work done by the gas. And so even though I have formula right now, you don't really need to do calculation yet. You need to know the concept, which the area under the PV diagram will be the work done by the gas. So this is for constant pressure. If the pressure is changing, then you just separate the process one by one until you approximate the curve into a straight line, and you learn all your calculus thing. So you know that even though when the pressure is changing, the work is still the area under the PV graph, which you have to calculate with integration instead of this simple formula, but the concept is the same. The work will be the area under the PV curve, okay? And the direction of the curve matters. If you are expanding, the gas is increasing the volume. It is pushing the piston. It is doing work to the environment. If the volume is decreasing, then the piston is compressing the gas, the environment is doing work to the gas, and the work is down to the gas, okay? Make sure you know if the volume is increasing or decreasing. Increasing volume, lose energy, do work to the environment. Decreasing volume, gas being compressed, work is down on the gas, work flow from environment to the gas, and the energy of the gas increase if there's no heat. If there's heat, you will see that it's more complicated. Any question? Direction matters, area matters. Now, if I have a process that is a loop, I go from this point to here with a blue curve and go back following the red curve. Will the overall work be falling out or in to the gas? Will the work done by the gas when it pushed out be bigger or smaller than the gas the environment do back to it when you compress it on the red line. Overall, is net work going out of the gas or into the gas? Oops. Hold on. 22. Okay, so the answer is B. Good job. So because when you are expanding, the pressure is higher in this case. So the area under the blue curve will be bigger than the area under the red curve. You have bigger work flowing out, smaller work flowing in, so overall work flows out, and the overall work is done by the gas. Okay? Any question? So to be more precisely, this is the work done by the gas when it expands, and this is the work done on the gas when it gets compressed back. You see, the work out being the area is bigger than the work in, and if you subtract them, because one goes out, one goes in, you subtract them, what you get is just the area inside the loop. So another important concept is that on a PV diagram, if you have a loop, then the work done by the entire cycle will just be the area inside the loop. You don't need to worry about the area under here anymore. It's just how big the loop is. If the loop is going this way, then you can tell it is doing work to the environment. If it goes out of direction, then the work is flowing into the gas. Okay? Any question? Okay, now more terminology. If the process involves constant volume, the volume is not changing, we call this isochoric. We call isochoric. I don't think you need to memorize this isochoric. You need to memorize isothermal, which is constant temperature, and adiabatic, which is no heat, but I will tell you that later. For isochoric, I think they all agree to tell you it is constant volume if you're doing an exam question. If the volume is constant, the process should not change its volume, and the V coordinate will always be the same, so it will look vertical on a PV diagram. It can go up or go down, both are called isochoric, and this is how it should look like on a PV diagram. Okay? So far, so good? So, next terminology, isobaric. Isobaric now means constant pressure. If you are heating a gas, in order to maintain constant pressure, you must also expand the gas, so the volume will not be the same anymore. But if we define the isobaric process to be constant pressure, it has to be horizontal because pressure cannot change along the line. It can go left, it can go right, but pressure cannot change. In this case, a practical way to do that is to let the gas expand when you heat it. So the volume increases, but the pressure doesn't change. Okay? Now, look at this. For isobaric process, you have to increase the volume. Then if I heat up a gas with the same amount of heat, I have the same amount of gas, same thing, but I heat it in a way that I don't allow the gas to expand, which is constant volume, isochoric, and I heat the gas in another way, which I maintain the pressure instead of maintaining the volume. Which way of heating the gas will increase the temperature more? We just spent a couple of slides talking about the work done by gas. Just like you need displacement to do work, for gas, you need a change of volume to do work. In this case, if a gas is expanding, work flow out of the gas, and that will decrease the energy. So if you add the same amount of energy by heat, but one loses energy by work and the other one doesn't, the temperature, meaning the energy of the gas, will end up differently. In this case, because the work flows out, the energy of the gas is not the same as heating isochorically. So at the end, the isochoric process will have a higher temperature if you just put in same amount of heat. Okay? So if you look at the change of temperature and the heat you add, with the same amount of heat, the isochoric process increases more temperature, and compared to isobaric, the increase of temperature is smaller. Okay? Now, does that mean the heat capacity for isochoric process is bigger or isobaric? Specifically, I'm asking molar heat capacity, so you don't need to worry about which one has more molecules in there. Same type of molecule, same amount of energy moles. So the only difference is one is fixing volume, one is fixing pressure. If you have a big heat capacity, it means it is harder to heat up. So if the temperature only increased by a little, it means the blue one is harder to heat up. If it is hard to heat up something, then it has big molar heat capacity. What is the question? Good. So you see, the constant pressure one has higher molar heat capacity. And that is always the case no matter which type of gas you're looking. The heat capacity of monatomic and triatomic is different, but the constant pressure one will always be bigger than the constant volume one. Any question? Good. Now, let's introduce gamma, which is the ratio between them. So it's a dimensionless number. It basically only depends on how many atoms is in a molecule. So it can help you characterize the gas property, and it will show up in some formula in your formula sheet. It will be 5/3 for monatomic gas, 7/3 for diatomic gas. You don't need to memorize it. You need to know how to calculate it in your final, but not for the midterm. It's just that you will see gamma all over the place, so I figured to introduce it earlier than later. But anyway, there's a thing called gamma, the ratio between them. So those two processes are the process that you don't need to memorize the name. The next one is very important, so we have to memorize the name. Isothermal process means constant temperature. Instead of maintaining the pressure, you maintain the temperature. So the pressure will change, volume also change, but they will change in a way such that the temperature doesn't change. If you expand the gas, pressure should decrease and temperature will decrease. So if you maintain the same temperature, Boyer's law is that they are anti-proportional. They multiply into the same number, which is nkBT. So this is an inverse proportional relation. You can again go backward, forward. Different particle number, different temperature gives you different line, but the shape should look like this. It's an inversely proportional line for constant temperature. Okay? If you maintain the temperature and particle number, increasing volume decrease your pressure, and decreasing volume increase your pressure. Okay? Any questions? So please remember isothermal, constant temperature. Thermal, temperature, easy to remember. Good. And the next one start with an A, adiabatic. So I think it's also easy to remember. Please remember that. Adiabatic means when you are changing the volume or pressure, there's no heat flowing in or out. That's called adiabatic. In this case, the graph will look similar to the isothermal one, but you know they should not be the same. For adiabatic, temperature can change, which isothermal is a constant temperature process. Okay? Now is the time to brainstorm. Let's compare isothermal and adiabatic. For the same change of volume, which I expand the gas in the same way, which one will end up with a higher pressure? Should it be isothermal or adiabatic? Adiabatic means no heat, so there's no heat. For isothermal, heat can flow in. Also remember, temperature has a meaning. It's the average energy of the gas. So if the gas number is not changing, temperature is not changing, the energy of the gas is not changing. If the energy of the gas is not changing, the amount of heat that goes in must equal the amount of heat that goes out. So the energy of the gas itself stays the same and the temperature stays the same. For adiabatic process, the gas just loses energy by doing work, which means the temperature will decrease. Energy, temperature, same thing for ideal gas, okay? So instead of energy stays the same, you know the temperature will stay the same. Instead of energy decrease, you know the temperature will decrease. So if you have the same volume, same particle number, and the temperature on the top is higher, the pressure will be higher. So that's why the top one will be higher in the pressure in the final state. Any question? Good. So because the pressure will be the same, the pressure will be higher for isothermal at the end. When you compare the two graphs on the PV diagram, even though both are a curve, you can tell the difference by comparing if you start with the same pressure and do same amount of change of volume, which one will be different. The easiest way to tell is that the adiabatic one will be steeper because the heat doesn't replenish the energy. So if you see the steeper one, that's the adiabatic, the flatter one will be isothermal, okay? It's not up and down. It can be different, but the adiabatic one will be steeper. Good. So you see that when we look at this thermodynamic process, there's three main characters. The energy of the gas, the heat that flows into the gas, and the work done by the gas. They are all energy or a form of energy transfer. So you learn that energy is conserved, and we have energy conservation for 9B version. 9A version is just a change of energy equals work. Now you just have a different form of energy transfer called heat, and you add it in there. So it's the same thing. I hope you guys understand energy conservation in 9A. It's just harder in 9B because heat is also involved. Okay? Any question? First law of thermodynamics. All right. So here we see that we have an equation that relates heat and work. It means that we can indeed change heat into work by using a heat engine. Instead of this one, which is harder to understand, I think this one is easier to understand. So you see that the candle here, or the burner, is putting heat into the engine, and the engine do work by pushing the piston. There is macroscopic motion on the piston, so that is work. The engine is doing work over here by pushing the piston, and the heat is flowing in over here by a stationary flame. Nothing is moving on here, so that's heat, and here there's work. There are friction that there's friction, so the engine doesn't speed out to infinity. But overall, you see, this is how you can turn heat into work. It may not be the most efficient way, but I think it's easy to understand. This is not the only type of heat engine. You just need to be a cycle because you want to reuse your engine. You don't want it to be single use. And you can design a cycle in many different ways. This is just one of the ways. So you see, in the beginning, the marbles are on the right, so the heat is over here, right on top of the flame. When the gas is right on top of the flame, heat can flow in, and then the pressure of the gas increase and expand. So that's why now the gas will expand and push the piston down. If you push the piston down or up, gas flow into the syringe through this pipe, and the syringe rise up. Then it tilted the engine, turns the marble or rolls the marble down here, which squeeze the air to the other side. Because now the air is not on top of the flame, it can cool down by dissipating heat into the environment. And by cooling down the gas, the pressure decreases again, which means the syringe will fall down, and then you are back to the initial state. So this is how this simple heat engine works. Note that for a heat engine, in the cycle, there can be heat flowing into the engine and also heat flowing out of the engine. It's not just turning all the heat into work. You have to dissipate some of the heat. Also, because it's a cycle, the volume will increase, decrease. There will be work, there will be a process that you do work to the environment, and there's also a process that the work is done back to the gas. The displacement will be the same because it's a cycle. However, work is not displacement. Work is force times displacement or pressure times the change of volume. So at this state, when the gas is hot, the pressure will be higher compared to this state, which the pressure is lower. So when you're doing work to the environment, the pressure is higher. Therefore, the overall work will be going out. You are doing work to the environment. You are turning heat into work because the work out is bigger than work in. So after you subtract it, it's still overall a net work flowing out of the gas, out of the engine. So this is how this heat engine works. Any question? There will be more complicated version in your final, but so far you just need to know there's a heat engine. And it's very useful. That's what turns our life from barbarian living in a cave into industrial revolution, heat engine. That makes the train move. And we still use them in your car. Not all things electric yet. And that's how our power station turn all the energy into electricity. So you will not, hopefully, I hope you will see an age without heat engine, but so far it looks like you will have to live with heat engine somewhere in your society. For heat engine, we are turning heat into work. Heat is usually not so useful because it's just hot. When it's summer, you don't want heat. Work can be useful. You can use work to move things around. You can use work to move a car. You can use work to turn on any electronic. Those are work. So turning heat to work is usually good for us in application purpose. But this kind of thing, is not free. It's usually not that free to turn heat into work. You cannot just turn something useless to something useful. So it is usually the case that the total work you do to the environment will be smaller than the heat you go in. Energy is conserved, so if you just subtract Q in, Q out, W in, W out, then of course they will be the same, energy is conserved. But the case is that we usually have no access to the expelled heat. When the heat goes out, it's useless. The heat will go out at a place that you have to have some water to cool down the heat engine, otherwise it will overheat. And that hot water you can make a hot spring, but after that, it's gone. You cannot turn this waste heat or heat waste into useful work. So that's why in the denominator, we just put in Q in. What we want to know is that if you just put in this amount of heat, how many percent of those heat can turn into useful work? The work that goes into the engine can be stored, so that's why we subtract it. We are not looking at just the work out, we also have to subtract work in. that do take away your energy from the environment. The overall work you can do with this engine is the net work out minus work in. So that's why it's on the top. And at the bottom, we just put heat input, not heat input out minus output. This is the definition of efficiency. So there's a theoretical limit, which you will learn later before your final. The current heat engine made by you engineers are way below those limit, like by 1 order, 2 order of magnitude. So work harder. You are not at your limit yet at all. All right. So is there any process that can turn all the heat involved into work? This is a trick question. Yay. It's a process. It's not a cycle. And I'm not asking a yes/no question. I'm hoping you to give me a process that turns all the heat into work. That would be very helpful because heat is useless, work is useful. If we can turn all the heat into work, that would be awesome. But what process can do that? Come on, you just learned it today. You just learned it. It's not, I mean, it is controversial. That's why I'm mentioning it. That's why I'm spending time on it. But if we are not asking for a cycle, we just want a process that turns all the heat that you throw into the process into work. Is that possible? And how do you make it? Steam. Yeah, we are going to talk about ideal gas because that's the only thing we know. Trend does not do that for sure. No. I don't, not a Dyson sphere, no. Dyson sphere turns photon into electricity, but you have to cool down the convert rate is not 100% due to some microscopic heat engine thing. Yeah, so no. Okay, it's fine. I don't know the answer before I learn it yet, so we are equally smart. Good. Consider a isothermal expansion. Isothermal means that the energy of a gas doesn't change, so the heat goes in must equal the heat goes out. So work equals heat, you turn all the work into heat. Okay? Energy of the gas is just the temperature, or temperature times how many gas you have. There's this factor of 3½ for monatomic gas. You will learn later that for different type of gas, diatomic, triatomic, the prefactor will be different, but overall, the meaning of temperature is the average energy of the gas. So if you have the isothermal process, it will turn all the heat into work. That's awesome. The problem is that it's not reusable. The reason we want a cycle for heat engine is because I just want an engine. I don't want a box that will expand to infinity. Then I have to feed it into a bigger trunk every day. That's not useful. But if you just want a process, yes, isothermal expansion turns all the heat into work. But if you have a cycle, then no, it's impossible to turn all the heat into work by a cycle. For a cycle, if you have to go back to the initial state, then some of the heat must flow out as wasted heat. Okay? Any question? Yeah.
Where did the 3 halves come from? That equation?
So 1/2 comes from 1/2 mv squared kinetic energy. 3 comes from you have 3 dimensions. You can move in 3 ways. Good. Any other question? So you already learned equipartition theorem. Every mode of energy gives you 1/2 kBT. So for a monatomic gas, you have 3 modes. You have 3½ kBT of energy. If you have n of them, you have n times that energy. So this is a heat engine. Heat engine turns heat into work. If you reverse the process, you can have your refrigerator. How do you make a refrigerator? Refrigerator is something very special. Usually heat goes from hot to cold. So if the outside is hot, inside is cold, heat should flow in, and at the end they should be equally hot. But we are in this nice room with AC, with air conditioning. So how exactly does the refrigerator keep pumping heat from low temperature to high temperature? One way to do it is like this. You can have a box of gas, which the temperature is the same as the temperature indoor, and then you can expand it. By suddenly expanding the gas, you cool down the gas, which allows heat to flow from the room into the box of gas you have. So now you absorb heat from this room, which is good. It will cool down the room. Later, you just somehow move the gas to the top, maybe by human, maybe by a machine. And now the gas is contacting the hotter reservoir. Then you can compress the gas, which will heat up the gas. And once the temperature of the gas becomes higher than the outside environment, heat can now flow from the gas to the outside environment. So this is how you pump heat from low temperature to high temperature. Of course, this is not free. You have to do work. You have to use work to expand the gas over here, and you have to do work to compress the gas over here. So overall, you still need to pay some price, but it's doable. You can have AC, you can have refrigerator. Those are wasting electricity. If you open the refrigerator in your room, the whole room will not be colder, it will be hotter because you're just wasting electricity. You can create a temperature difference inside the fridge and outside the fridge by plugging in electricity, but don't open your fridge. That's a waste of energy. So for a refrigerator, instead of efficiency, we care about different things. We care about how many heat we can pump from the room, from the cold reservoir, which we call it QC. How many heat we can pump out by the network we input to the refrigerator. So the bottom line is like the electricity you pay, and then the top one is the heat that you pump out at the end. If you can pump out more heat, then you have a better performing refrigerator. If you compare the definition, this is different than efficiency. As you can see here, work out, work in over Q, and here the work is at the bottom, and only the QC is on the top. So let's end of the lecture. I'll see you on Thursday. There's another homework due next Tuesday.